Hello students, in this video lecture series we will discuss all these cases. We will draw shear force diagram and bending moment diagram for each case. In previous videos we have solved all these cases, this one, and in this video we will solve this case simply supported beam subjected to a concentrated load. The shear force is positive if it tends to move left portion upward relative to right portion. Suppose this is a beam and this is left part, this is right part. On left part I am applying force upward like this. So we can see here again we are applying force like this. So this is left part on which force is applying upward, and this is the right part on which force is applying downward. If this is the case, it is a positive shear force. Again we will see the shear force is positive if it tends to move left portion, this is the left portion, upward relative to right portion. This is another case which is opposite of this. If this case happens, then it is a negative shear force. The bending moment is positive if it tries to sag the beam. If left portion of the beam is considered positive movement, works out to be clockwise. So this is a section and it is the left part, and bending moment direction is this side, clockwise, and we are seeing this is a beam which is sagging. If this case happens, it is a positive bending moment or sagging bending moment. Again we will see the bending moment is positive if it tries to sag the beam. If it tries to sag the beam, if left portion of the beam is considered positive movement, works out to be clockwise. So we are seeing this is clockwise movement and we are taking it as positive. If it is opposite of this one, it is hogging. So we will see it is negative bending moment because at the left portion bending moment is anti-clockwise. This is positive bending moment in which beam is sagging. This is negative bending moment in which beam is hogging. This is a question: simply supported beam subjected to a concentrated load. So AB is a beam which is simply supported at point A and B, and there is a load W is acting which is at a distance of small a from point A. So first we will calculate reaction RA and RB. We know it is in equilibrium, so we will apply the condition of equilibrium for the coplanar forces. It is two-dimensional. So three conditions of equilibrium are: sum of horizontal force is 0, sum of vertical force is 0, and sum of movements is 0. So we can see here there is no horizontal force, so it is 0. Now we will come to this equation. RA is upward, RA, W is downward, minus W plus third is RB, RB equal to 0. Summation of forces should be equal to 0. Now we will take movement. We can take movement at any point. This is A, B, and we are saying this point capital C. I am considering movement at point A in anti-clockwise direction, I am taking positive equal to 0. So W is the force and A is the perpendicular distance, and we are taking movement about A. So this force will rotate it like this. Again, this force will rotate it like this, and it is rotating in clockwise direction. So minus W into small a. Second is, we are taking movement about a point and force RB is acting upward. So this is force and this is the perpendicular distance. Perpendicular distance is L. So force will apply here and it will rotate like this. Again, force is this and distance, perpendicular distance is L. We are taking movement about point A. So it will rotate into anti-clockwise direction. So we have taken symbol in anti-clockwise direction, sign is positive, plus RB into L, and the summation should be equal to 0. So RB equal to W A upon L. Now we can find out RA. This is first equation, this is second equation. So RA minus W plus RB value is WA upon L, summation should be equal to 0. So RA equal to W minus WA upon L, L minus A upon L equal to WB upon L. L minus A is B. So RA is WB by L and RB is WA by L. RB is WA by L. Now we will write shear force and bending moment equation for portion AC. After that we will write equation of shear force and bending moment for portion CB. For portion AC, for portion AC, so consider a section between A and C. We are considering this is a section. And the distance of this section from point A is x. We will see towards the left of this section, we are naming it y dash. First we will write for shear force. Shear force we will see towards the left of this section there is one shear force which is RA equal to WB by L. WB by L, and it is acting upward, that's why it is positive. So, it is constant. Shear force at x equal to 0. If I will slide this section to this side, x will reduce, and this is the general equation. There is no x in this, so it is same WB by L, and shear force at x equal to small a. If I will slide this section to this side up to C, so x will increase and x will become equal to a. This is the general equation, there is no x, so it will again same WB by L. So, from A to C, shear force is constant. Now we will write bending moment equation. Bending moment is the force into perpendicular distance. This is force, we will see towards the left of this section. This is force and the distance is x. So, bending moment equation is force WB by L into x. If these sections come to this side, x will reduce. So, bending moment at x equal to 0. If this section will come to this side, x will reduce at 0. This is the general equation, put x 0 in this equation. So, bending moment is 0 and bending moment at x equal to small a. If I will slide this section to point C, so x will increase and x will become small a. So, we will put small a here because this is the general equation. So, bending moment is W B A upon L. So, this is linear equation, linear variation bending moment has linear variation. We can see from this equation it is x. So, it is linear and it is constant. So, we will draw shear force diagram and bending moment diagram for portion A to C. We can see here from A to C portion, shear force, this is shear force, it is constant, and bending moment diagram, bending moment at point A x equal to 0 is 0, so it is 0, and at x equal to A at up to the C point, it is WAB by L. WBA or AB both are the same. After solving for the portion AC, we will solve for the portion CB. So, we will take a section y dash between CB and the distance of this section from point A is x. We can solve this question from right portion also, but we are maintaining one strategy to solve the question from the left side. So, this is x, this is section y dash between C and B. we will write shear force equation. At the left of this section, there are two forces, one is Ra and another is W. Ra is W B by L, it is upward, that is why it is positive, and W is downward minus W. So, we will solve it. W is common, B by L minus 1 equal to minus W A by L. So, shear force at x equal to A, we will slide this section and we will go to point C. So, x will reduce and it will become A. So, shear force at x equal to A is same minus W A upon L, and shear force at x equal to, we will slide this section to this side up to the point B. So, x will increase and it will become equal to L. So, at x equal to L, shear force is same minus W A upon L. So, bending moment equation. Bending moment equation is force into perpendicular distance. So, this is a section. At the left of this, there is a force Ra. So, force Ra into perpendicular distance, which is x, R A into x. Force is positive, that is why it is Rax. Second force at the left of this section is W, it is downward. So, force into this distance. So, this distance is, x minus A equal to this distance. Again, x minus A will get this distance, force into this perpendicular distance, minus W because it is downward, x minus A perpendicular distance. On solving, we will get W on solving we will get W B upon L into x minus W x minus A. So, bending moment at x equal to A. So, this section will slide between C and B. So, we will slide here up to point C. So, x will reduce and it will become A. So, we will keep x equal to A in this equation. W B A upon L minus W A minus A equal to W A B upon L. So, this is the bending moment at point C. Now the bending moment at point B. So what we will do, we will slide this section to this side, x will increase and its length will become L at point B. So bending moment at x equal to L, W B L upon L minus W L minus A equal to 0. L minus A is B and it will cancel L, WB minus WB equal to 0. We can see here from C to B, shear force is WA by L and bending moment at point C where x is equal to A is WAB by L, and at x equal to L bending moment is 0. So this was the case for simply supported beam subjected to point load. In next video we will discuss simply supported beam subjected to uniformly distributed load over entire span. Thank you.